Okay. Now, same way, how to make the gallium arsenide p-type. So I'm going to use beryllium or magnesium, which is a group 2 element, which can be used for the formation of p-type material. So beryllium is the lightest p-type dopant for gallium arsenide, and deep implantation of atoms can be accomplished. So the same thing, instead of silicon, I'm going to use beryllium. Beryllium is a group 2 element. The group 2 element means it will have 2 valence electrons in the outermost band. Gallium requires 3. Beryllium has only 2. So definitely one electron is shortage. So when all the doping atoms you add beryllium, one electrons will be shortage. Absence of electron becomes hole. So I can say accumulation of holes will take place. That in that case, you make the gallium arsenide to be a p-type material. See, remember, whenever I'm going to have a gallium arsenide as such, it is going to be intrinsic. It is pure. So whenever I want to increase the conductivity of the gallium arsenide, I'm going to add dopant. If I want to make N-type, I'll be adding group 4 element, mostly silicon. If I want to make it P-type, I'll be adding group 2. Group 2 is beryllium or magnesium. Magnesium can also be used to make it a P-type. That is also be, you can also use it, but beryllium is very light. So the doping of the gallium arsenide using beryllium will become easy. The process is going to be very easy. And gallium arsenide is a direct band semiconductor. So direct band means you can see the energy band diagram. So the conduction band minimum and valence band maximum occurs at the same time. So the lowest, the conduction band minimum and the valence band maximum will occur at the same time, or it will occur in the same momentum. I can say that. So when these two are going to be different, I'm going to be called as an indirect band gap materials. So gallium arsenide is a direct band gap. Direct band gap means directly I can find the forbidden energy gap, Eg equal to Ec minus Eb. When the minimum is somewhere here and maximum is somewhere here, it is called as indirect band gap because they are occurring at different momentum. But for direct band gap, the energy conduction band minimum and the valence band maximum will occur at the same momentum. See, the x-axis is momentum. And the momentum is same for both the conduction band and the valence band, right? So when these two are going to happen at the same momentum, this device is going to be called as a direct band gap semiconductor. So this means little momentum change is necessary for transition of electron from the conduction band to valence band. So this property makes gallium arsenide excellent light emitting diode. So conventional silicon and germanium will not emit light when you provide forward bias or reverse bias. But this gallium arsenide is a unique material which is going to emit light when you are going to forward bias the device. So this direct band gap ensures that you have a light emitting capability for your gallium arsenide. But if you take silicon and germanium, they are indirect band gap material. So the light emitting property will not be present in silicon and germanium, whereas it will be present in gallium arsenide. Please understand, all light emitting devices, if you take a full, when you go to optical communication where light is going to be everything, all the devices in optical communication will be made up of gallium arsenide or combination of group 3 and group 5, gallium phosphide, indium phosphide, indium arsenide, gallium arsenic arsenide phosphide, indium gallium arsenide phosphide. So lot of group 3 and group 5 elements are there, and when you make different combinations of all these elements, you get special type of materials which are exclusively used in optical communication. So remember why silicon and germanium is not emitting light. Why gallium arsenide is emitting light? Very simple. Gallium arsenide is a direct band gap semiconductor, but whereas silicon and germanium are going to be indirect band gap semiconductor. See, for emission of light, the conduction band minimum and the valence band maximum should occur at the same momentum. There should not be even a slight change in the momentum. There is a momentum change. You cannot expect that device to act as a light emitting device.